This difference between chart convergence and Earth convergence helps to explain why great circles are concave to the parallel of origin on a Lambert's chart. Imagine a Lambert's chart. Take two meridians, say 20 degrees apart. Now consider three different latitudes, say 47 north, 45 north, and 43 north. The parallel of origin will be 45 north. Draw straight lines joining the meridians at these latitudes. You can see that the three rhumb lines, which all cut the meridians at right angles, are parallel to each other. And also the three straight lines are all parallel to each other, although at different latitudes. So, the angle between the rhumb line and the straight line is the same in all three cases. What is the angle between the rhumb line and the straight line called? It's called half-chart convergence. What is the formula for calculating it? The angle between the rhumb line and the straight line equals half the change of longitude times the sine of the parallel of origin. So let's now calculate it. The change of longitude is 20 degrees, and the sine of 45 degrees is 0.7071, which comes to 7.071 degrees in all three cases. Now a different question. Let's consider the angle between the great circle and the rhumb line. This is conversion angle. What is its formula? The formula is that conversion angle equals half change of longitude times sine mean latitude. Again, let's calculate it. For conversion angle, of course, there will be three solutions, one for each of the three latitudes. Now let's plot each of these angles upwards from the rhumb line at each latitude. This will give us the initial great circle tracks. At 47 north, it is about 7.3 degrees. At 45 north, the parallel of origin, it is 7.071 degrees, the same as the straight line. And at 43 north, it is about 6.8 degrees. Now let's also plot these angles in from the right-hand end, and draw the great circles joining them. This is why a great circle appears as a straight line at the parallel of origin, but is concave to the parallel of origin at any other latitude. The straight lines always make the same angle to the rhumb line, whatever their latitude. But the angle that the great circle makes to the rhumb line depends on its latitude. There's just one final point to make on this diagram. Look at the amount of curvature of the rhumb line compared to the straight line. It is approximately 7 degrees in all three cases. But look at the amount of curvature of the great circles compared to the straight lines. It is about 0.2 of a degree at 47 north and 43 north. It is a much smaller amount, about 1/30th the curvature of the rhumb lines. So, whilst you need to know that theoretically great circles are concave to the parallel of origin, in fact, for all practical purposes, including plotting, you can treat them as straight lines on a Lambert's chart. And now we will deal with just one more idea, which is often useful in dealing with exam questions. On this diagram, positions A and B are joined by a straight line, a great circle, and a rhumb line. At the meridian, midway between the longitudes of A and B, all three lines will have the same track angle. So, let's summarise. We looked briefly at Lambert's scale, but there was no requirement to calculate how scale changes. If there is less than 16 degrees of latitude change between the standard parallels, then Lambert's charts are constant scale, such as on this topographical chart. But for smaller scale charts, where there is a greater change of latitude, they are not. We saw that chart convergence is the difference in the inclination between two meridians on the chart, or the change in a straight line track between two meridians on the chart. This is the equivalent to Earth convergence, but reference to a straight line on the chart, not a great circle. We saw that there is an equivalent of conversion angle on the chart. It is called half-chart convergence, and it is the difference between a rhumb line and a chart straight line. We then worked through a couple of practical examples, and found that you treat these just like convergency and conversion angle problems on the Earth, except that the rules apply to the straight line on the chart, not the great circle. We then showed that this difference between conversion angle and half-chart convergence explains why great circles are concave to the parallel of origin. But we emphasised that whilst you need to know that theoretically great circles are concave to the parallel of origin, in fact, for all practical purposes, including plotting, you can treat them as straight lines on a Lambert's chart. And finally, we said that at mid-meridian, the straight line, the great circle and the rhumb line all make the same track angle. This concludes the lesson on Lambert's scale and convergence. The next lesson will consider practical plotting.